This chapter is on temperature and heat. It's on the general section of what we call thermodynamics. And to begin, we need to define what we mean by temperature and heat. Temperature is a measure of the average random kinetic energy in a substance. There are two parts to this you have to think about. One is the concept of average, and the other is random energy. Now, most of this energy is in the form of kinetic energy, but some can be randomly distributed as in the form of potential energy, like the compression or vibration of molecules or the rotation of molecules. And we need to first address how we measure temperature and look at the units of these various temperature scales. First of these is the Fahrenheit scale. Now, in the Fahrenheit scale, many of you recall that 32 degrees Fahrenheit is freezing water in the English system, and 212 is boiling. So we have, for Fahrenheit, we have freeze water at 32 degrees Fahrenheit, and we boil water at 212 degrees Fahrenheit. And you'll notice that this is a difference of 190 degrees. You should remember both of these temperatures. You're responsible for knowing them. And the first thing you might ask is, where do we get these weird numbers? Was water not used as a standard? Obviously it was not, because these numbers are just plucked out of thin air. And there's something very, very interesting that this goes back to. You might say that when Fahrenheit came up with his scale, he picked the coldest thing he could think of to make it 0 degrees, so he would not have to deal with negative temperatures. So you can say, well, what is the coldest thing? Well, obviously he picked something to be 0 degrees Fahrenheit. And he picked some other standard to give him 100 degrees Fahrenheit. Can you imagine what these two are? Well, it's there in your notes. And you can see that 0 degrees is freezing seawater. In other words, ocean water that's frozen, which is much colder than regular water. And he picked 100 degrees for the human body, which is really 98.6 as we take it today. But he chose that to be 100 degrees, thinking because his thermometers were not exact. So this was based on a human scale. This is in keeping with the concept of the foot as long as our foot, an inch the width of our finger, the cubit, the distance from our elbow to the tip of our finger, the yard, our nose to the tip of our finger, and all of the British system, going back to the human scale and relating things to the human body itself. Well, obviously this is not a very good temperature scale. We know now that temperatures go far below freezing seawater, and therefore you have negative temperatures. And we want to define something based upon pure water. We do that with the Celsius scale, and as you might guess, the Celsius scale, erroneously sometimes called centigrade, but properly called Celsius, has 0 degrees for freezing water, 100 degrees for boiling water. And then it turns out that 273.15 degrees below 0 is absolute 0. In other words, that's where the motion of all molecules stop, and there is no random motion. Therefore, since there's no average random energy, we would say that's as cold as anything can be. So then if we go on from that, we might say, let's redefine it based upon absolute 0. And we do that with the Kelvin scale, which by definition takes 273.15 and adds it to Celsius. So we use the same degree difference, 1/100th of the distance between freezing and boiling water. But we now add this to it, so 0 degrees Kelvin is now at absolute 0. And everything else is now well defined, and you can see that 373 would give us boiling water. In what we do, all scales will be in terms of degrees Kelvin. And we need to do that because that leaves us with a good standard going from 0 to 100 from freezing to boiling water. And also from redefining that as the base where we have no negative temperatures. So now 0 degrees Kelvin is absolute zero, and 273.116 is actually where we have the triple point of water. And this is the formal definition of degrees Kelvin now. We start with 0 degrees Kelvin, and it turns out that the triple point, now what is the triple point? The triple point of water is where steam and water and ice can all coexist in equilibrium with one another at a particular exact temperature and pressure. And it's at 1/100th of a degree above this previous temperature. And for the test, you're responsible for remembering the Fahrenheit scale, the Celsius scale, and these various temperatures. In other words, you must remember that the triple point of water is 273.16. Kelvin is originally defined as 273.15 degrees plus Celsius, and how Celsius is defined from 0 to 1/100. Now, thermometers are used to measure temperature, and they primarily use the linear expansion of a substance. It could be mercury, or it could be other things. Mercury is good because mercury is a liquid, and so it will move through the tiny capillary inside a thermometer, giving you an exaggerated scale for the small expansion of that liquid. Because mercury is the only metal or substance like that that's really heavy that is a liquid at ordinary temperatures. But the optimal thermometer is a constant gas thermometer using an ideal gas. We'll talk more about what an ideal gas is later, but you can kind of picture it as being an ideal gas. Our temperature conversion is formed by these three equations, and you can rederive these from these numbers that you have up here. But on the test, you'll be given a Celsius number, and you have to convert it to Fahrenheit or vice versa, which uses this equation, and from Celsius to Kelvin and back, which uses this equation. Now, heat is the mostly random energy that's within a substance, and it's the energy that flows due to a difference in temperature. In other words, if you have two objects together, and one's hot and one's cold, and they're in contact, then obviously over here we have molecules moving very rapidly, and over here they're moving very slowly. Then at this interface where they touch, these molecules hit this and preferentially lose energy, lose this random energy to the cold side. But the cold side would never give up energy to the hot side. That simply doesn't happen, as we'll see with the second law of thermodynamics. Now, the standard scientific international units for heat is the joule, because all energy is measured as a form of joule. So it's the SI units of energy in general. But we have some other units that are very useful. For example, a calorie is the amount of heat necessary to raise the temperature of 1 kilogram of water 1 degree Celsius. So if we take, again, using water, which is our standard for the international system, and we take 1 kilogram, we want to raise its temperature 1 degree Celsius, then this requires how much energy? 1 calorie. C-A-L-O-R-I-E. Doesn't look much like an A there. There we go. Requires 1 calorie. So 1 calorie will heat us up 1 degree. So if we take this kilogram, how much do we need to go from 0 up to 100 degrees? We need 100 calories. And we can say, well, what is a calorie? Well, we're going to define a calorie in just a minute in terms of the joule. But you'll notice that this calorie is used with a capital C. There's another calorie that the chemists use that has a lowercase c, which pertains to a gram of water and not a kilogram. And so this capital C calorie is 1,000 times the small c calorie. So it's this large calorie, or what is normally often called a kilocalorie, more properly, that we eat when we eat food. So when you eat a 100 calorie banana, you're eating 100 kilocalories or 100 capital calories. You're eating enough calories to heat this kilogram 100 degrees. Another common unit that's used in the English system, and certainly in America a lot, is the BTU. And you've probably heard a lot about the BTU. The BTU is another unit of energy like the calorie, and it's the amount of heat necessary to raise a pound of water 1 degree, 1 degree Fahrenheit. So it's based on the pound and the degree Fahrenheit. And those are the, I'll give you the conversions for these back to joules in just a minute. But these are the units that we'll have, and you can see that the BTU and the calorie are very useful when we talk about heating things. And in particular, heating things, and we can relate those to water. Water retains a lot of heat, and we'll see that when we look at the scales of water relative to other substances.